Okay, so let's try 36 and 18.3 because I forgot to tell you a word, so I'm telling you a word now. The word I'm telling you now is potential function. And the reason I forgot to tell you this word is this is kind of a physics word. So a potential function is the function whose gradient your vector field is. Does that make sense?
So it's
Probably
active
not.
and partial of f.
So if you have a vector field, right, it is possible that that thing is the gradient of something, right? The function it's the gradient of is called the potential function. That really is kind of playing the role of an antiderivative, right? So what we have in number 36 is they tell me the gradient of a function f is the vector field 2x e to the x squared sine y, comma, e to the x squared cosine y, right? And then they tell me that I should find the change in f between 0, 0 and 1, comma, pi over 2. And they tell me to do that in two different ways, by computing a line integral and by doing this other thing. Okay? What's the other thing? Like, what's the easy way to do this problem?
Computing f, just plugging values in one.
Yeah. Find a potential function, plug those 2 points in, subtract, right? Fundamental theorem of line integral.
0, 0, so it would just be plugging it into the other function, right? You wouldn't be, there would be like no difference.
There might be a height at 0, 0.
Okay.
Right, keep in mind when you evaluate a function at 0, that's not the same thing as multiplying a thing by 0. But here, let's do this. Let's find our potential function, right? So I should think to myself what?
Well, the left one is gradient of dx, and the right one is gradient of dy.
Close. Wrong word, right thought. This is the partial with respect to x of f, and that's the partial with respect to y. So eyeballing, what's that thing seem like it's got?
Dx squared. That's definitely something it has.
Yeah, there's probably an e to the x squared, right? And then like a sine or a cosine of y, right?
It's probably sine because the cosine's going to be turned into a...
So what I might think is I might look at this guy, my e to the x squared cosine y, and think, okay, if that's fy, right, then f should be that antiderivative of that stuff with respect to y, right? And so I get e to the x squared, it's the antiderivative of cosine. Sine? It's either sine or minus sine. Minus sine, right? Sine.
So
And then there should be a plus c, which might be a function of x, right?
But since you know that's a gradient, you don't need to monkey around, right?
Oh no, you still want to consider this, right? So the reason you still want to consider this thing might actually contribute to the partial with respect to x. And then I would have to figure out what that h function actually is. You guys see that? In this case, I don't have to, right? You guys all see that? But it would be a good idea. So the reason I don't have to here is that if I differentiate this stuff with respect to x, what do I get? Yeah, I get the I component of this thing they told me was a gradient vector. So h prime is 0 at least. You guys see that? Which tells me this thing doesn't depend on x, it's an honest constant. You guys see that? So what I've found is that f of x and y, right, is e to the x squared sine y plus some constant that's actually a constant, right? You guys all good with that? Okay, now what?
We now know it's...
Yeah, so now we need to evaluate at our 2 points and subtract, right? So I'm really taking that thing. I'm taking my e to the x squared sine y and evaluating between 0, 0, and 1 comma pi over 2. And I really put your plus c in there just for kicks. We'll see that you don't need that here in a second,
Oh, yeah, because
because you'll subtract it off, right? So once you plug your numbers in here, you get e to the 1. What's the sign of pi over 2?
oh,
One?
that's 1.
Cool. E minus, oh, whoops, e plus c minus. And then you plug in 0, 0. So 1 times 0 is 0 plus c. So you get plus c minus c. So you get out of this e. Right? Which means that the gradient, right? If you go from 0, 0 to 1 comma pi over 2, right? And I did apparently beginning and end, right? The vector field, the gradient vector field does e units worth of work for you. You guys see that? Or the function f's height changes by e between these two values. You guys see that? It goes up. Cool. Questions, Steele? No? Cool. All right, and to work the line integral, so if you were going to do the other half of this problem, what path do you pick between 0, 0 and 1 comma pi over 2? Yeah, it doesn't matter, because it's...
Yeah. It's conservative.
Yeah, it's conservative,
It's
and
path
thus path
independent.
independent.
Yep.
You guys see that? So, it doesn't matter which path you pick, so what's the easiest path to make between 0, 0 and 1 comma pi over 2?
Straight line.
Yeah, straight line motion, this thing. So your r of t, right? If you were going to do the line integral, the r of t should be t comma pi over 2t, right? And t should range between 0 and 1. You guys good with that?